This is Unit 10B, Part 6, and this is the Lagrange form of the remainder, also known as the Lagrange error bound, or also known as Taylor's theorem remainder. Okay, so let's just begin. If we are given f of x and it is a power series in x, if we have a partial sum, what we have is a sum of the first few terms of the series, okay? Now, the tail is the rest of the series after that partial sum that you took. And the remainder is the number you get by adding all of the terms in the tail together. Okay? So, the tail is also terms. Okay? The partial sum is a sum of first few, and this is the sum of remaining terms. Okay? So these are, the tail is just the terms itself, not added together. So what do we have? We could say that f of x is equal to a partial sum plus some remainder. So let's just write something out here. We could have the actual f of x would be equal to an approximation of some sort plus the error. We could say that. So this is actually equal to, let's say you would use, let's say, for example, you sum the first three terms, okay? Or third degree. How about that? For example, if we had f of x, we could say it's equal to this partial sum, third degree Taylor polynomial, plus some remainder. And note this remainder uses 3. It does include the fourth term and beyond, but we use that notation to note how many we used for the approximation, okay? So the error is the error you make by assuming f of x is the partial sum, okay? So the error is the same number as the remainder. Now, even though that's obvious, it's not subtle. So what we want to do is make sure that you understand that the error is the same number as the remainder. But what we want to talk about and address is this error bound. And it is a number known to be greater than the absolute value of the remainder. So we have a boundary on our error. For an alternating series, of course, if you've met the 3 hypotheses, the absolute value of the first term of the tail is the error bound. And we did that. We took that next term and we said that was the boundary on our error. Then we got to the integral test for convergence, and that improper integral was our error bound. Now we present the Lagrange remainder. The Lagrange remainder is the error. It is exactly equal to the first term of the tail, but with its derivative evaluated not at x equal to c, which is the center, but at some number z, which is between c and the actual value of x at which you are evaluating the function. As this value of z comes from repeated application of the MVT, there's really no way of knowing exactly what z equals. It says not often, but it's pretty difficult. But we can find a number that is an upper bound for the derivative between c and x. And that's what we call our Lagrange error bound. So Taylor's theorem introduces a function f, and it's differentiable through order n plus 1. And it's in an interval containing c, and then for each x in the interval, there exists some number z between x and c, such that this here, this remainder right here, is here. Okay? So this is where we chop it off. Okay, at whatever point we do that to. So that's why this and this value of n are the same. Now, one useful consequence of Taylor's theorem is that this remainder here is going to be bounded by this expression. Now, it looks very confusing, but we will use it and it won't be so bad, okay? The only real new thing is this maximum value of the n plus 1th derivative evaluated at z. And that's what I just read here. And it is between x and c. This gives us a bound for the error. It does not give us the exact value of the error, and we call this boundary the Lagrange form of the remainder, or it can also be called the Lagrange error bound. Now we will address some AP standards, and then we will go on to do some examples, okay? So some of the series problems use different notations. There was one question where students were asked to show this right here. And the grading standard showed this below. And as you can see, this is that difference between the approximation and the actual value, okay? So if you have right here, if you have the actual value equals your approximation plus some error, okay, then, and that's what this is the actual, and this is our approximation, okay? And you could say you stopped at whatever n was. Then, if you took the absolute value of your actual minus your approximation, you can see that you will have your error. Okay? Now, that is what this is right here. This is the error, and this is a bound on the error. Okay? Okay. And so you can see here that they used the 4th degree Taylor polynomial to approximate f of 1/4. So what did they do? They went to the 5th derivative and evaluated it on some x value between 0 and 1/4. And this is what's interesting. You can just look in your calculator and you just have to find that highest value that you can see on this. So you just put that fifth derivative of f on this interval 0 to 1/4, and you want to choose the highest value on 0 to 1/4. Now, what we can say, and that's just for that term, that doesn't even include this or this. And then that's actually what they did. They found that to be 40 in this problem. They still had 5 factorial, 4 to the 5th, from the 1/4 to the 5th. And then there it is, and it was less than 1/3000. Without knowing that problem, I guess it didn't make much sense, but I think it should help. Let's go ahead and take a look. The function f has derivatives of all orders for all real numbers x. Assume that f of 2 is 6, f prime of 2 is 4, and so forth. Write the third degree Taylor polynomial for f about x equal to 2, and then use that to approximate f of 2.3, and we'll use 3 decimal places. So let's go ahead and find the third degree Taylor polynomial. You can use p or you can use t. Let's use t today. The third degree Taylor polynomial, and that's going to equal, of course, our first term is always f at whatever c is, so f at 2, plus, now we'll take that first derivative, multiply it by x minus 2, and of course divide by 1 factorial. And most of the time you don't see either the 0 factorial or the 1 factorial here. You just don't see them. And we usually don't begin writing them until 2, but it's never wrong if you do. Okay, now let's take -7, so minus 7 x minus 2 squared over 2 factorial. So far, we have 3 terms, but we need to get to the third degree. And do you see that we are only at the second degree? So it's not the number of terms, but it's the degree. So just making sure you get that. Plus 8 times x minus 2 cubed all over 3 factorial. So we are going to use this to, and this is exactly equal to that because this is the third degree Taylor polynomial. It is not an approximation. But now we will use it. F of 2.3 is approximately equal to T3 of 2.3. which is equal to 6 plus 4 times 2.3 minus 2 minus 7 times 2.3 minus 2 squared over 2 factorial plus 8 times 2.3 minus 2 cubed over 3 factorial. And I got that to be equal to 6.921. Okay? So we just approximated, and we don't even know what f is. Look at this. F of x equals question mark. We don't know what it is, okay? The fourth derivative of f satisfies this inequality. Well, what did they just give you? They just gave you 9 is the largest value for the fourth derivative, absolute value, of the fourth derivative of this function f of x for all x in the interval 2 to 2.3. They don't even tell us where it is, but it's on this interval, okay? So this is really important. That third degree remainder is actually equal to that fourth derivative of z x minus 2 to the fourth. What did I write here? All over 4 factorial. Do you see that it's this next term? Right here is where this came from, right here. Okay? Now, we won't have to go and get that. First of all, we don't even have the fourth derivative, okay? But what can we say? We can say that that error is bounded by 9. There we go. Let me put, and 9 is that maximum value right here on that interval. So we actually have that boundary, 9 times x minus 2 to the 4th, all over 4 factorial. That's our boundary. So now the remainder, after approximating with the third degree Taylor polynomial, that absolute value is less than or equal to 9 times 2.3 minus 2 to the 4th power, all over 4 factorial. And that is equal to 0.0037375. And that is less than or equal to 0.003. And I don't think anybody gave us, oh, this is, yes, okay. So you could just use that, okay? Okay. So let's go ahead and use our answers in part A and B to find an interval such that f of 2.3 is between two values, and we will give 3 decimal places. So the reason why this is helpful is because that is what our approximation is within the actual. Okay? Error within an interval about 0, 0, an interval about, yeah. Okay, so what could we do? We could say f of 2.3 is somewhere in between, and so now what we're going to do is take our value here, our approximation 6.921, and we're going to add 0.003 to that. So 6.921 plus 0.003, and then 6.921 minus 0.003, and you come up with 6.918 and 6.924. Okay? So this value are these values, and this is our approximation is here. Okay? So now we know that our error is within 0.003 of actual. Okay, that's what that means. Okay, could f of 2.3 equal 6.922? What do you notice? 6.922 is in that interval. So you could say yes, since 6.922 is an element of 6.918 to 6.924. So we could actually write that here of what our actual value is. We could go ahead and just write it like that. Okay. Could f of 2.3 equal 6.927? No, it cannot. And the reason is 6.927 is not an element of this interval. It is outside of this interval. Okay, so let's go ahead and take a look at example 2. Okay, we just have 2 more examples. Let f be the function given by f of x equals the sine of 5x plus pi over 3. And let p of x be the third degree Taylor polynomial for f about x equal to 0. Okay? So, find p of x. So we need that p3 of x. So first things first, we have to write down f of x, f prime of x, f double prime of x, and then the third derivative, okay? And all of these are going to be evaluated at 0. So we have the sine of pi over 3, which of course, but you know me, I'm going to, of course, always make one of these, and the cosine is a half, and the sine is root 3 over 2. So the sine of pi over 3 is root 3 over 2. F prime of 0 would be 5 times the cosine, which would be 5 times a half. F double at 0 would be the sine of pi over 3, which is root 3 over 2, multiplied by negative 25. So that's a negative 125 over 2. And then f triple would be a negative 125. Whoops, I did the other derivative here. So this is just a 25. Goodness. 25 right here. So that's a negative 25 times root 3 over 2. And then f triple prime evaluated at 0 would be a negative 125 over 2 because it's negative 125 times a half. Okay, let's do it. Third degree Taylor polynomial. Remember, always is your first term, f of 0 or at the center, plus, okay, we're going to take that 5 halves and we're going to multiply by x, of course, x minus 0, and it would be over 1 factorial. Now let's take that negative 25 root 3 over 2. Don't forget about your 2 factorial, and there's your x squared. Let's do that one more time. Minus 125 over 2 times 3 factorial, all multiplied by x cubed. Okay, we're going to work with this. Okay, we're going to work with this third degree Taylor polynomial. Use the Lagrange error bound to show that f of 1/15 minus p of 1/15 is less than 1200. Okay, 1 over 1200. And we're going to be using this up here. So let's first find that fourth derivative of x, and that's a positive 625 times the sine of 5x plus pi over 3. Okay, now since, and this is really important, the sine of any theta is always less than or equal to 1, because it's between -1 and 1. And this is for, and I'm going to use this new notation, for all theta, okay? Now this upside down capital A stands for all, okay? Now you don't have to know that. You could have said, written out for all, okay? So for all theta, this is true. The sine of theta is always less than or equal to 1. So what is that? We could now say that the fourth derivative of x is less than or equal to 625 times 1, which is 625. Okay? So that remainder, after approximating with a third degree polynomial, this is actually about equal to f of x. That's what we were approximating. Is equal to the fourth derivative of x times x to the fourth all over 4 factorial, that absolute value. And here is our Lagrange boundary. That's less than or equal to 625, which was the maximum value of the derivative anywhere on the interval, times x to the fourth all over 4 factorial. Okay? So what could we say? Therefore, the absolute value of the remainder of 1/15, that means the remainder after approximating with a third degree Taylor polynomial evaluated at 1/15 is equal to the fourth derivative evaluated at 1/15 times 1/15 to the fourth power all over 4 factorial. And here it is less than or equal to 625 divided by 4 factorial times 1/15 to the fourth power. And actually, if you work this out, that is equal to 1 over 1944. Let's write our final statement. You could say, thus, the actual value of f of 1/15 minus our third degree Taylor polynomial approximation at 1/15 is equal to the remainder, right? All of that sum, and then that is actually bounded by 1 over 1944, and that is less than 1 over 1200. See if I can kind of get this just a little bit higher. I did not do a good job there. But just try to take some time and think about all of this. And we'll just rewrite this for all, and maybe in a different color. And that concludes the Lagrange error bound, and then we will just talk a little bit more on error and conclude Unit 10B.